Well, it's actually quite opportune to give a talk about the Rosetta mission because it more or less to the day is 20 years since the launch of Rosetta. The opening slide has actually got an awful lot of artistic license because although comets do have a lot of water, at least in the form of ice, they certainly don't have water as I've shown there, so that's artistic license. Equally, comets have a lot of fairly advanced organic molecules, but not, as shown in the bottom left-hand corner, cellular structures, at least as far as I'm aware. Right. So the outline of the talk, why the interest, something about comets, Comet 67P in particular, the Rosetta mission and the Philae lander. What did the mission discover? And in particular, what could it tell us about the origins of life on Earth? And then turn to asteroid missions. Are they actually more fruitful? They're certainly much easier to rendezvous with. And lastly, near-Earth objects and potential problems. So why the interest? Well, as I'm sure all of you know, comets and asteroids are largely leftover bits of material that formed from our solar system. So they haven't suffered the same changes that have occurred on Earth. So that they haven't suffered from weathering, volcanic activity, tectonic activity. They're not, of course, entirely pristine because comets, when they get close to the Earth, close to the Sun, and asteroids are, of course, bathed in radiation from the Sun. And that, of course, does affect the material, particularly on the surface of comets and asteroids. But nonetheless, they are much closer to the material from which the solar system formed than the Earth itself. So they can tell us a lot about the proto-solar nebula. Of course, for a long time, interest in comets was very, very different. And asteroids, of course, were unknown until probably, the last 100 years. For a long time, comets were seen as harbingers of doom. Of course, they are spectacular, but they're infrequent. Obviously, people were aware of the stellar patterns in the sky and the occasional wandering of the planets as they move around the sun. But comets are infrequent, albeit spectacular, and a lot of people regarded them as harbingers of doom and essentially objects to be feared. Halley's Comet, which famously appeared shortly before the Battle of Hastings, shows a different recognition of comets. I suppose a typical kind of politicians and leaders that they choose whatever scenario they like to meet, whatever it is they're doing. So because William was very successful, he thought that Halley's Comet actually was heralding his success rather than a harbinger of doom. They are, of course, spectacular objects, and Comet Hale-Bopp is actually by far the best comet that I've seen, with the naked eye. This was in 1997. And another one, Comet Lovejoy, Santiago de Chile is the photograph taken. And you can see that the sky is, relatively bright, but yet the comet, particularly the comet tail, of course, is clearly visible. As I said, the comet's leftover bits of the solar nebula, and the planetary system, of which we're a part, of course, was formed from the giant cloud of gas and dust that collapsed to create the sun, planets, and moons 4.5 billion years ago. So here's an obvious picture of the gas and dust surrounding the central star, which is for us is the sun, and the material rotating around, from which, of course, our planetary system formed. And for a long time, in fact, up to about 30 years ago, many astronomers believed that a planetary system, planets around any star, would be very, very rare. That situation has changed quite dramatically. And now it is thought to be the exception, not the rule, if a star actually doesn't have any planets. And the name exoplanets is how planets around other stars are now referred to. So we have the nice schematic of the solar system with the planets, and we have the asteroid belt between Mars and Jupiter, and then much further out, of course, the Kuiper comet belt beyond Neptune, and then very distant is the Oort comet cloud, with very little known about any of the objects within the Oort cloud. Of course, from time to time, comets that are either in the Kuiper belt or even much further out in the Oort cloud that get perturbed by one of the giant planets and move to an orbit much closer to the Earth. Comets are largely made of ice and dust. Asteroids are now mainly rocky. So, of course, the spectacular thing about comets is their tail, and that arises simply because when the comet is a long way away from the sun, the ices on the comet stay as ice. But as the comets move around the sun and get closer to the sun, then the ices evaporate, sublimate off the surface of the comet, and the radiation from the sun pushes the ice and some of the dust from the comet away from the sun. So the comet tail is always pointing away from the sun. So again, it doesn't matter where the comet is, you will always see the tail pointing away from the sun. So this is basically just saying what I said a moment ago, except introduce the word coma, which is the material that comes off the surface of the comet, but doesn't actually get pushed away into the comet tail, or at least not rapidly. So you get this huge cloud of gas and dust around the comet nucleus, and that's the coma. Sorry, whoops. Got too many bits here. Okay, that's basically what I've just said. So a little bit more about comet properties. Well, they're actually, and surprisingly, quite small. Most of them just measure, the order of 10 miles across. Much smaller than asteroids. The biggest asteroid is of the order of 500-600 miles across. So comets are a pretty small piece. Although the nucleus of the comet is small, the coma, that's the gas and dust around, can be as much as 1 million miles across, or 1 million kilometers, yeah, 1 million miles. And the tails can be 100 million miles, which of course is why they are so spectacular. Most comets are very dark as the ices are coated with dark organic material. And the ice is thought to be mainly water ice, but other ices, ammonia, carbon dioxide, carbon monoxide, and methane are very common. So, how are comets discovered? Well, in the early days, people had to use photographic emulsions, which they photograph the sky over a period of a few days or weeks, and essentially looking for objects that move relative to the background stars. So this was actually how 67P was discovered. So the comet has moved relative to the background stars between these two images. Of course, today it's much, much easier. Photographic emulsions replaced by CCDs, and one can automatically scan the images in order to detect anything that has moved relative to the background of the stars. Well, I said Rosetta launched roughly 20 years ago, so just on March the 2nd, 2004. And of course, comets are not easy to reach. They're often moving as much as hundreds of miles a second, not miles per hour, but hundreds of miles per second. So there's no way that you can shoot a rocket with its payload from the Earth and go directly to the comet. That would be impossible. So the only way that you can rendezvous with the comet is to go on a kind of roundabout journey where you go around the Earth, that's Mars, and essentially you're catching up with the comet. So one of these lines represents the Rosetta mission, the other the comet. And eventually, if you've got the mathematics right and your control system is good enough, then you will rendezvous with the comet. Okay, and that's the only way you can actually get to them. Rosetta was at the size of a human, so that's 5-6 feet. And this was one of the first images of Comet 67P taken by Rosetta. And although this is, of course, now an old image, about 10 years old, it's still quite spectacular to see the comet in so much detail. And you can just see, I keep on losing my cursor here. Whoops, sorry, let me go back one. Too many controls. You can just see the ice is being sublimated from the surface of the comet. Here, forming what were just the beginnings of a comet tail. Now, notice how the density of comets is extremely small. I mean, less than 0.5 gram per cc, whereas water is, of course, 1 gram per cc. Because of a lot of ice is less dense than water, so it's not surprising that the density of comets is relatively low. But I think it's also as well because comets are relatively porous, they're not kind of lumps of granite. So although they're relatively small, you wouldn't want one landing on your head. And here you can see the size of the comet relative to, Big Ben and the Tower of London. Here's another nice image of the comet. And again, you can now see more clearly the ice and some dust which comes off of the ice being, well, not ejected, but sublimating off the surface. Well, this was a hoped for touchdown site, site J, now known as Agilkia, for the lander Philae. So Rosetta, the kind of mothership, as it were, went into orbit around the comet. And then the idea was that Philae, which is much smaller part of Rosetta, would land on the surface. Here's another nice image of the comet, and you can see a boulder here, which is about 40-50 meters across. So although the comet overall isn't huge, nonetheless some of the boulders on it are quite large. This is the view from Philae before it was actually released. So Philae is looking at where it's going to go, as it were, and then Philae is launched off the comet. Sorry, not off the comet, off the Rosetta, and here's an image of Philae on its way to the comet. So the image, of course, taken from Rosetta, and this is where it was going to land. Well, as I think many of you will know, the landing wasn't, at least initially, successful. The problem is, of course, that landing on a comet is very, very different to landing on the Moon or Mars. For the Moon and Mars, because they're big objects, the gravitational field is high. So the whole problem is stopping any lander from crashing into the Moon or Mars. So you have to have some way of breaking the descent of the lander. For comets, because they're so small, the gravitational pull is extremely small, and a lander such as Philae would, unless it had some way of securing itself to the comet's surface, would simply bounce off. Well, essentially that's what happened. The various mechanisms that Philae had in order to land and stay on the surface essentially failed. One of the reasons that it was unsuccessful is that the scientists and engineers had underestimated the amount of dust on the surface, and it turned out there was about 15 centimeters of soft material on the surface, or at least where they intended to land. So you can see that anything intended to grab at the surface and lock Philae to the surface would have problems when it tried to grab the soft material. So what actually happened is that Philae bounced and didn't land on the surface as in this artist's impression, but landed about 1 kilometer away, and very unfortunately landed close to a cliff which obscured Philae's view of the sun. Here at the bottom here is an image photograph taken when they eventually located Philae, and you can see that one of its legs is kind of sticking up there. And the problem was with it being in the shadow, the solar cells were not able to recharge. There was not sufficient sunlight, and the only power they had on board was that which they'd had at the time Philae left Rosetta, because Rosetta was still orbiting the comet at this stage. So what did the mission discover? Obviously not as much as they'd hoped, because of the failure of Philae to land properly on the surface. Well, Rosetta, orbiting the comet, spotted phosphorus and organic compounds such as glycine. And we'll mention glycine quite a few times in this talk. It's actually the simplest amino acid, and the elements like phosphorus and the amino acid, glycine, were found in the haze around comet 67P. And there's been huge interest over the years in the discovery of amino acids in various objects, and I'll return to that later. And this always raises the point as to whether life on Earth was seeded by comets, by asteroids, which landed on Earth in the early phases of the Earth's history. Philae itself, although it had very limited time to do any experiments, nonetheless did discover ammonia, hydrogen cyanide, hydrogen sulfide, formaldehyde, methanol, etc., etc. I mean, all molecules which are, very common here on Earth, you'd find in, most laboratories and often actually at home. Philae was able to actually send out like a radar signal to penetrate the comet, and those signals were able to be bounced back to Rosetta. And it was then, by analyzing that, it was determined that the comet has roughly 2.5 parts of ice for about half a part of dust or rock. So comet 67P is very, very icy. And that, as it has in previous studies, raised the question, did comets deliver water to Earth? So let's look at 2 key experiments. Where did the Earth's water come from? Well, when the Earth first formed, it's very likely, because water is ubiquitous throughout the universe, that the Earth contained a huge amount of water. But it's believed that the Earth, when it first formed, would be extremely hot. Therefore, most, maybe all the water evaporated off. Now, not everybody accepts that, but it's a reasonable hypothesis that the Earth would have lost a lot of water, maybe not all, but certainly a lot of the early water. So, was it present when the Earth formed, or was it delivered by comets and/or asteroids? And how can we tell? Well, the way that's been done for a number of years is to measure the amount of what's called heavy hydrogen. Hydrogen, which is proton, is an atom, there's a proton with an electron around it. It has an isotope called deuterium, which is proton plus one neutron. Ordinary water, two hydrogen and oxygen, H2O. Heavy water is D2O. And it's called heavy water, but of course it's not that much heavier than ordinary water because oxygen is so much heavier than hydrogen. So most of the weight in water is the oxygen. So heavy water is only a little bit heavier than ordinary water, but nonetheless, the term is still used today. Now, the Earth's ocean does have one atom of deuterium for every 6,500 atoms of hydrogen. Previous observations of comets and material from comets, material in the coma around the comet, can be observed and analyzed by telescopes here on Earth. So the result that comets tend to have far more deuterium to hydrogen, heavy water to ordinary water, than we find in the Earth's oceans, rivers, lakes, etc. There's only one comet, Comet Hartley, which has roughly the same amount of heavy water as we have here on Earth. So people start to believe that comets were unlikely to be the major contributor to water here on Earth. However, the deuterium to hydrogen ratio in asteroids is generally very close to that in the Earth's oceans. So although asteroids have lost a lot of their water, over the billions of years which they've been going around the sun, they, in the early days of the solar system, asteroids would have contained a very large amount of water. And in the so-called heavy bombardment phase of the solar system, when there was lots of material going around the sun, which didn't actually go into the sun or into planets, then a lot of that material would have impacted the Earth. So for the first couple of billion years of the Earth's existence, there would have been a huge number of comets and asteroids landing here on Earth and would have contributed enormous amounts of water. This is related to the Rosetta probe mission because this is an image of the asteroid Lutetia. This was photographed by Rosetta on its journey to 6 or 7P. And you can see that it's kind of a much plainer, less interesting object than at least Comet 67P. Okay, well, the second experiment, key experiment that Rosetta Philae was supposed to carry out, was to try and answer one of the key questions in the origins of life here on Earth. Now, amino acids are essentially the main building blocks of all of us and of all animal life here on Earth. And amino acids are actually important in plant life as well. Now, we tend to think of proteins as being the key thing, for example, in our diets, but proteins are made up of amino acids. So amino acids are absolutely crucial. Now, one of the interesting things, key things about amino acids is that they have what's called left-handedness. And I'll explain that a little bit more in a moment. But the question that has been around for 150, 160 years is, where did this left-handedness arise? Okay, well, what do we mean by it? Well, if I'm giving a talk, it's much easier to demonstrate. But if you look at your hands, and I put my hands up, assuming you can see them, I'm not sure. So what's the same? Well, we've hopefully all got 4 fingers of a thumb. And so to some extent, our hands look just the same, left and right. But in fact, they are very different, because what you cannot do with your hands is to move them around such that they superimpose identically one over the other. So one's left and one's right, and as it were, never the twain shall meet. What I did here was to photograph my left hand in a mirror. So I put my left hand up, and then there was a mirror behind it, took a photograph, and what it looks like is my right hand. Okay, so our right hands are mirror images of our left hands, and of course, vice versa. So although our hands are identical in many ways, they have a unique handedness. And technically that's known as chirality. And it's exactly the same for every amino acid in our bodies. They all have a left-handed configuration. So this shows in a little bit more detail. If we look at the bottom part first, amino acids are actually fairly simple. There's a carbon atom with a hydrogen attached, a carboxyl group, COOH, an amino group, NH2, and R. R determines what kind of amino acid it is. So R will be different for things like valine, tryptophan, leucine, etc., etc. But as I say, there are two configurations. Here's a left-handed one, and here's a right-handed one. And although it's not easy perhaps to picture it, there is no way, just as you couldn't with your hands, that you can move these around so that they totally overlap each other. They're entirely distinct forms, and technically these are known as enantiomers. And again, one's a mirror image of the other. Right, homochirality is where you have equal number of lefts. Sorry, homochirality is not that, sorry. Let me start again. Homochirality is where you have just one sign or one-handedness. For example, all your amino acids are left or all of them are right. But if you're making a solution of amino acid, it doesn't matter which one it is, let's say tryptophan, if you get the chemicals off the shelf and pour them into a flask to make up whatever it might be, then you will make up equal lefts and rights. And that's technically called a racemic mix. However, chiral molecules of biological origin in all us, or animal life, or plant life, are invariably homochiral, composed entirely of one enantiomer. And for self-replicating molecules, it only works if you have the same handedness. And as I said a few times, for life forms here on Earth, amino acids all have a left-handed configuration. So how did this homochirality arrive in living things? Well, Louis Pasteur, 1848, first discovered that molecules essential for life, say, for example, amino acids, have these two mirror image forms. And ever since that time, people have never understood why or how it's arisen. But if it hadn't have done, then life wouldn't have been possible here on Earth, or indeed anywhere in the universe, because in order for biological life to exist, you have to have all chiral molecules of the same handedness. Now, in the laboratory, you can selectively destroy either the left or right-handed molecules preferentially. So if you destroy the left ones, you leave primarily right, and vice versa. So how do you do it? Well, it's actually, you could do it for a few quid. You use circularly polarized UV light. Now, electromagnetic waves, light waves, for example, the light that you can see if you're looking at your screen, the light consists of electric and magnetic fields. And the electric field is the key one for us. The number of forms of what are called polarization of the light. One form which perhaps people are more familiar with is linear polarization, in which the electric field is essentially oscillating in a line or in a plane as it's moving from the source of light to your eyes. There's another form of polarized light, and that's circularly polarized light, in which the electric field is actually rotating around as the light moves from the light source to your eye. And there are two forms, left-handed and right-handed. And if you have left-handed circularly polarized light and you shine it on our flask of equal left and right, then it will preferentially destroy the left-handed amino acids, leaving you with excess of right. Or use right-handed circularly polarized light, shine it on your flask of equal left and right, you'll preferentially destroy right-handed, leaving you with an excess of left. Now, to get circularly polarized light, it's very easy. Those of you who are photographers may have actually bought for a few quid from Amazon or other retail suppliers a circular polarizer filter. And what it does is to ensure that any light from whatever you're trying to photograph goes onto your CCD detector in your camera, is circularly polarized, which then won't affect the sensitivity of the CCDs detecting the light. If you have linear polarization, such as you might get from light shining from a snowy surface or a lake surface, then that can alter the image. So circularly polarized filters, few quid, ultraviolet light, yeah, no problem getting that. So doing this experiment is actually easy and cheap. Well, that's in the laboratory, but what about for us? We weren't actually produced in the laboratory. I mean, maybe a few hundred years, perhaps most people might be produced in the laboratory, but certainly not at the moment. So what's the source of circular polarization? There doesn't appear to be any suitable sources on Earth. So if circular polarization is the trick for making amino acids primarily for us left-handed, then, where is this circular polarization? Well, in 1998, fortuitously, we reported the discovery of very high levels of circular polarization in the core of the Orion Nebula, where stars and presumably planets are being formed. These were levels of order of 20%, and it was totally unexpected. What we proposed as a result of discovering this circular polarization, that it had implications for biomolecular permacorality. That is why we all have left-handed amino acids. Anyway, here's two images of the Orion Nebula. On the left, just a visible image, and on the right, an image taken in the infrared. And as I said, what we discovered is regions of high circular polarization. If I just click one more time, they'll rotate. So here was left-handed circular polarization, and here was right-handed. Now, one of the key things is that each region of left and right is vast compared to the size of our solar system. So our solar system on this kind of scale would be smaller than a pinprick, meaning everything in it, any amino acids, whatever, would see one side of circularly polarized light. So is this then the way that we all ended up with left-handed amino acids? Well, it does provide a naturally effective way of doing it, or at least initiating an excess-handedness. although people still argue about, how the process did start, everybody seems to be happy that once you actually have an excess of maybe only a few percent, doesn't need to be much more than that, then as life develops, it will indeed then go to 100%. So it's just getting that initial excess. I think I said earlier on that in the early phases of the Earth's existence, so-called heavy bombardment period, a lot of material from asteroids, comets landed here on Earth and could well have had, I'm pretty sure did have, this excess for us of left-handedness. So our observations suggest that the left-handedness we find on Earth should be common throughout the solar system. You perhaps remember that I emphasized, just go back, that these regions were very large compared to the size of our solar system. So anything in our solar system should have the same handedness. Return to that later. Right, well, not everybody, a lot of biochemists, don't accept this scenario at all. They argue that there is no need to have any mechanism for producing the left-handedness, at least as a precursor to life. What they argue is that the left-handedness is a consequence of life. So they argue life formed, and of course nobody still knows quite how life itself did develop on Earth, but they argue that when life developed on Earth, almost by a statistical quirk, it went left-handed. And once you get an initial excess, then that kind of, through what's called autocatalytic reactions, ends up being close to, or indeed 100%. Well, that's an argument, but why I think it's a dubious one is for the following. Meteorites are discovered quite regularly on the Earth's surface, and one of the most famous ones is the Murchison meteorite, which fell near a town called Murchison in Australia in 1969. And like a number of meteorites, it was rich in organic material, including a large number of amino acids. Now, again, what's absolutely key in this story is that some of these amino acids are very rare or not present on Earth, so they didn't come from contamination. Contamination of meteorites is a problem because obviously when many people discover a meteorite, the first instinct is to pick it up. And what they do then is they contaminate it. There's a sweat, skin cells from their hands, and that makes it then very difficult to distinguish from what was intrinsic to the meteorite and what has simply been transferred from whoever handled it. But if the meteorite actually contains amino acids that are very rare or indeed not found normally on Earth, then you can be pretty sure that they were indeed intrinsic to the meteorite. And what people discovered was there's an excess of left-handed amino acids and enantiomers of about 8%. Now, the meteorite is about 4.5 billion years old. And of course, life on Earth is only a few million years. So for 4.5 billion years, way, way before life on Earth started, amino acids on this meteorite already had a left-handed excess. And there's about 7 or 8 meteorites which have sufficient amount of amino acids on them in order to do the test. And all of them have had left-handed excess of amino acids. So those people who argue that the left-handedness arose simply through life itself and wasn't a pre-requirement, as it were, have to explain why meteorites have the same handedness as ourselves. Because, of course, going back to what I argued a few slides ago, because the region of left or right circularly polarized light is so vast compared to our solar system, everything in our solar system would be based in the same sign of circular, and for us, that would mean everything would be left-handed. Well, Philae, one of the experiments to detect any excess-handedness. Well, has it? No, the experiment was not carried out as it simply ran out of power, which was a great disappointment to those of us who are interested in this topic. On the other hand, if it hadn't run out of power, had discovered amino acids with a right-handed excess, then everything I've talked about today would be deemed a load of rubbish. So we await with bated breath for any other missions which are able to determine any left or right-handed excess, and hopefully they will all be left and none right. Now, the only amino acid detected was glycine, which is not chiral. Glycine, if you remember, and I should have pointed out at the time, I apologize I didn't. If you remember the schematic, as it were, of the amino acid, the molecule, then if R, that was the thing which tells you what kind of amino acid it is. If R is a hydrogen atom, you get glycine. But if R is a hydrogen atom, it means that the left and the right, are actually identical. So glycine isn't chiral. Although it was disappointing that the experiment on the chirality wasn't carried out, it's still true that comets and indeed asteroids could be providers of life, certainly must have brought key molecules, things like amino acids, to the Earth's surface well before life as we know it developed. Asteroids are now being studied far more often. They're actually far easier to reach than our comets. But before we look at asteroids, let's just mention briefly some other comet missions. Stardust in 2004, that flew through the coma of comet Wild 2. And what that had on board was, on a screen, some aerogel, which is kind of very sticky stuff. And the idea was that it would fly through the coma of the comet, and molecules, any dust, whatever present, would adhere to the aerogel. That aerogel, the sample was returned 2006, landed in the Utah desert, and there were a number of organics present. But one of the problems was that because the aerogel on the spacecraft was going through the coma at a huge speed, it didn't actually collect a representative sample of what's actually present in the coma. But nonetheless, it did detect glycine. Glycine keeps on coming up all the time. We'll come back to that a little bit later, but it's not chiral. The other one, which probably some of you will be aware of, was Deep Impact in 2005. This is when a large mass was shot into the nucleus of Comet Tempel 1, and the debris and crater were analyzed. And there was more dust and less ice than expected on this particular comet, and the dust was seen to be much more like talcum powder than the sun. As I said, glycine is commonly found, and it's very abundant in our own bodies. Glycine is what makes collagen. It's what's called a structural protein. It's important in skin, hair, nails, etc. So glycine, which is commonly found on comets and on asteroids, is what's also commonly found and is the most abundant amino acid in our bodies. In fact, glycine can also be found in interstellar space, and this was, I think, discovered maybe 50, 60 years ago. Right, asteroid missions. Hayabusa 2 collected samples, just over 5 grams. And this was returned to Earth July 2019. And it detected a wide variety of organic molecules, including 20 amino acids. However, there was no excess of left or right, unfortunately. So they were all what's called racemic. It did detect glycine, but glycine is not really racemic because it's not chiral. The lefts and rights are equal. What it did discover, though, was uracil, which is very important information and function of our RNA, and niacin, which is vitamin B3. So amazing. Well, I think amazingly perhaps that you get amino acids, you get things which are important in our RNA, and things like vitamin B3. So these asteroids, which have been around for an awful long time, actually contain things which are common, in our bodies. Yeah, the most recent one, in fact, just the last few months, was the Bennu mission, in which material from asteroid Bennu, yes, the asteroid, was returned to Earth. And here's some of the material. And this was the material, or the returned back to the Earth. And that collected quite a little bit more than the Japanese mission, 100 grams. So quite a bit more. But what you've got to remember is that the Murchison meteorite was 100 kilograms. So meteorites are much easier to detect, perhaps traces of molecules, whatever, because of the sheer size of them, the amount of material. Whereas this material that gets returned to the Earth from, in this case, asteroids, is a few grams, perhaps up to 100 grams. Well, what has Bennu discovered? What have people discovered from Bennu? Well, first of all, it's extremely dark. Only 4% of the light that hits it is reflected. Again, lots of hydrocarbons, lots of water, not kind of flowing around or not necessarily in ice form, but locked up in minerals like clays. Again, unfortunately, unlike meteorites where excesses of left-handedness is quite common, any of the amino acids found in Bennu are racemic, that is equal left and right. And this just says that although left-handed isovaline excess up to 20% been found in Murchison, no left-handed enrichment was found in the Bennu sample. One of the things about Bennu that have kind of made people a bit curious about its origin is that they begin to believe that from the composition, it was perhaps part of an ocean world that was destroyed in the collision. So although, we tend to say, well, asteroids are bits of rocky material that was left over when the solar system formed, that didn't go into planets into the sun. Clearly, some of them will have resulted from collisions between objects in the solar system and their fragments left over from those collisions. Okay, well, finally, near-Earth objects, carriers of doom, question mark. Well, yes, I mean, people have been worried for quite some time that the Earth could be subjected at some point to a catastrophic collision with, what are commonly called near-Earth objects. That is, any object that's comes close to the Earth and potentially could strike the Earth. And some of the objects that occur quite often once a year can have as much as 4-meter diameter. Every 5 years, 7 meter, and every 1,000 years, 50 meters. Objects with a diameter less than about a meter are called meteoroids. Okay, if they're bigger than that, then they tend to be called asteroids. But meteoroids are any objects which are no bigger than about a meter. And they seldom make it to the ground to become meteorites, burning up in the atmosphere. Now, the amount of energy these things have is huge, not necessarily because of the size, but because of the huge speed. So a 7-meter asteroid, so one reaches Earth's atmosphere in 5 years, has the same energy as the atomic bomb dropped on Hiroshima. Now, fortunately, of course, a lot of that energy is dissipated in the upper atmosphere. You know, the asteroid explodes, and only a fraction, about a third, is released low in the atmosphere. Impacts, of course, take place as we speak. An atmosphere is subject to bombardment and can often be clearly seen. Oh, my internet connection unstable. Often have that. Comet Shoemaker-Levy hit Jupiter 1994. What actually happened, because of the huge gravitational pull of Jupiter, it caused the comet to fragment, and so different fragments landed on the surface. The most famous example, of course, is the huge asteroid, thought to be about 10 kilometers in diameter, which hit the Gulf of Mexico and had an energy estimated to be 10 billion nuclear bombs. I mean, that 10 billion nuclear bombs was a hell of a lot. It was about 66 million years ago and led apparently to the death of the dinosaurs. A number of you may have actually seen one of the meteors that's clearly visible still on the Earth's surface, because of course a lot of the craters get worn away by the weather, etc. But the meteor crater in Arizona is still pretty spectacular, and that was thought to be a meteorite about 50 meters across, and the energy about 1,000 nuclear bombs equivalent. So pretty massive. And then much more recently, 1908, the Tunguska event, where a large area of a forest in Siberia was destroyed, and that's thought to be about 20 to 30 times the Hiroshima bomb. And much more recently, looking at some of your slides from your chair earlier today, or this evening, notice you've got a talk about the Chelyabinsk meteor, and here are some dramatic images taken apparently by car cams, and you can see that a lot of the energy is clearly dissipated in the atmosphere, which is fortunate. But nonetheless, this meteor caused quite a lot of damage because shock waves generated in the atmosphere by the explosion can, let's say, damage buildings, etc., etc. And there are quite a lot of people injured, but no fatalities apparently. So impacts can produce shock waves, tsunamis, earthquakes, apparently initiate volcanic activity. And large enough ones, such as the one leading to the death of the dinosaurs, can send dust high into the atmosphere, changing the climate of the Earth. So to finish off, how do you avoid impacts? Well, the first thing, of course, to do is to discover objects which might be on a trajectory which would bring them close to or indeed impact Earth. And there are a number of telescopes around the world now surveying, monitoring the skies. For example, Pan-STARRS in Maui, Hawaii is one such telescope. And once you've discovered an object which looks potentially dangerous, then you need to alter their orbit. One of the early ideas was to send up a rocket and detonate a nuclear bomb nearby. Well, that's a bit dicey because you don't quite know what's going to result, and you actually may make matters worse by some of the fragments being more closely aligned with Earth than perhaps the initial object. As a test of the technique, NASA's DART project, just 2022, flew a object into one of the asteroids of the double, so this Dimorphos and Didymos. Dimorphos is viewed as a moon of Didymos, and what DART was able to do was to alter the motion of the moon, and apparently it was pretty successful, and people now see this as the way in which you can alter the trajectory of a near-Earth object. Clearly, of course, the thing to do is to detect these objects when they're far enough away that they only need a bit of a nudge in order to steer them clear of the Earth. The closer they get to Earth, then the more you've got to nudge them in order to avoid the collision with the Earth. So near-Earth objects, telescopes such as pan-STARRS, are extremely important in making sure that the Earth stays safe. So on that good note, I'll thank you very much. Thank you.
Great, thank you. Thank you very much, Jim. If you could stop sharing for a moment, but you might need to go back to your slides on any questions we've got.
Okay, where do I start? I'll stop sharing.
Just stop sharing for a minute.
Yeah.
And thank you very much indeed. One of the disadvantages of Zoom meetings is that we can't all give you a round of applause in real terms, but we do have a tradition here that we give you our reactions. Turn your cameras back on, everybody, as well, and either a virtual clap or a camera clap, please, for Jim, first of all, for a wonderful talk. Thank you very much. Yeah, you're getting a few virtual claps there as well.
Yeah, thanks.
Great. Let me just go to my gallery view so I can see everybody. Right, so thank you very much, Jim. That was fascinating and wonderfully illustrated as well. Some real food for thought there. As ever, I'll kick off with a question, then I'll hand over to the floor. I hope you've all got some questions ready for Jim there. Going right back to the beginning, Jim, a very, very basic question, really. Comets versus asteroids. I mean, most of us know that asteroids are rocky and that comets are icy, but is this division really, is it kind of definitive? Is it never the twain shall meet, or is it really just two extremes of the same thing? In other words, are there comets which are quite rocky but have a lot of ice, and asteroids that are quite icy but have more rock, if you know what I mean? Or are they really two distinct separate objects altogether? Or is there a kind of, you know, a scale of
I think it's a gradation from one to the other. So some asteroids are much icier than others. Equally, some comets don't have as much ice, for example, as Comet 67P. I mean, presumably a lot of it is due to the history. I mean, comets which have come in orbit and close to the sun for millions, perhaps billions of years, you know, will have lost quite a lot of their ice. Closer to the sun will have lost not all, but a lot of their ice in the billions of years which they've been going around the sun. But yeah, they're a gradation between you know, comets and asteroids. But comets tend to be smaller.
I mean, the reason I ask is because we're always, you know, right from when I was a child, I learned about the asteroid belt, you know, between Mars and Jupiter and this kind of thing, and they're all asteroids and they're all rocky, and the comets come from the outer solar system, from the Kuiper and beyond. And that kind of, it reinforces this idea that they're two completely different objects. But even within the, let's say within the asteroid belt, are there some asteroids that are more icy, have more ice than others? They're not just all balls of rock, are they?
No, no. And I mean, they have, for me, a surprising amount of ice on them, or
Right.
in them. So, yeah, I mean, they're not lumps of, well, they're not granite, but they're not lumps of granite, if you take my meaning.
No, no. Okay, good. And the other thing is just a more general question, summing up from what, that this whole thing about handedness and the
Mm,
potential for meteorites or any objects striking the Earth and actually seeding the Earth
mm,
with the precursors for life. I mean, unfortunately Philae didn't quite do what it was we hoped for reasons we understand.
mm,
And it's to be, and you mentioned, there will be other missions, and we will crack that nut eventually. We will get the full data back,
yeah.
hopefully, but we're going to have to be patient. But in the meantime, the evidence that we've got so far, all the data that's been collected, where do you think, not necessarily you personally, but where does the academic community, the scientific body of opinion sway in terms of seeding, panspermia, or whatever it's called?
Yeah.
Or, is the weight of evidence and is the majority of opinion moving towards the idea that probably life on Earth was not simply spontaneously started on Earth, but came from elsewhere and therefore other places? Or are there enough sort of people who say, no, 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 there's no evidence for that yet? We've got some, but we're pretty convinced that at the moment, life on Earth, we know it's unique, but it began uniquely on Earth and it wasn't anything to do with, as it were, alien invaders.
Yeah.
What,
Well,
what do you what do you think?
well, it is very divided. I mean, you're right. There are a lot of people who believe that, life developed on Earth, um, but it had to develop from something.
Yeah,
I mean, some of the molecules, which are abundant in space, I mean, fairly complex molecules have been discovered in interstellar space, um, for decades.
mm,
And, to imagine the Earth didn't actually have any of these molecules when it formed just doesn't seem to make sense.
no,
And some of the amino acids, particularly the alpha methyl amino acids, um, are actually very stable. So again, when people say, "Oh, well, yeah, when these things crashed into the Earth, then any amino acids would have either been destroyed, but clearly they don't because they're found on meteorites, or if not destroyed, somehow um, uh, they wouldn't have ended up with a left or a right-handed excess. But I mean, that is clearly found. But yeah, I mean, not everybody um, accepts the scenario we've put forward. Um, I mean, there are a number of alternatives, but I have to say, they none of them, at least in my way of thinking, are anywhere near as good as the circular polarization. I mean, for example, there is one that's been mooted a number of times, and that is in beta decay. That is, commonly called radioactive decay, in which a neutron is converted into a proton plus an electron, beta particle as it's called in radioactivity, uh, plus an antineutrino. Now, it so happens that radioactive decay is governed by what's called the Wig force. There are four forces in nature: gravity, electromagnetic, the strong force, which is what keeps a nucleus together, and the weak force, which is responsible for radioactive decay. Now, the weak force is essentially chiral, amazingly, and the electron in radioactive beta decay always spin with a left-handedness.
ah,
Don't ask me why, because I don't think anybody knows. Well, I certainly don't know. And the other amazing thing is that left-handed spinning electrons are more likely to destroy right-handed amino acids, leaving a left-handed excess. So people say, oh, that's it then. early Earth, lots of radioactivity, lots of left-handed spinning electrons. These destroy right-handed amino acids. There's your answer, left-handed amino acids.
Mm.
Now, the problem with that is that when anybody's looked at it in detail, the effect is about 1 in 10 to the 17. That's 1 with 17 zeros after it. So it may well be true that the mechanism exists, but it is so weak that I don't think anybody plausibly believes that you explain the left-handedness. But yeah, there are other views, and I don't know whether it's because a lot of people in kind of biochemistry, origins of life stuff, don't like astronomy. So anything where astronomers argue that's very relevant to life here on Earth maybe tends to be ignored. I don't know.
Mm. Fascinating. I mean, you know, that's for me, it's either side of the coin. If we don't believe in the seeding idea, then life on the Earth is unique, and
Yeah,
and we are just the
yeah,
result of that. If it is seeded, then it means that it's probably widespread
yeah,
among,
yeah,
well, not just the
yeah,
galaxy, but probably the
yeah,
entire universe. And
yeah,
I'm minded of Carl Sagan, who said whichever is the answer, whether we're alone or we're not alone, meaning
yeah,
by inference, the seeding
yeah,
principle. Whatever
yeah,
the answer is, either of them, it's still wonderful. It's still
yeah,
incredible. Yeah.
yeah. I
Thank you
mean,
very much.
well, if I just add slightly to that, I mean, interesting thing is, and I think a lot of people increasingly leaning to this view. There's a difference, of course, between life evolving, with whatever, and intelligent life like us.
Yeah.
And I think a lot of people, now believe that um, intelligent life might actually be fairly rare for a number of reasons. Um, but that still doesn't argue against life itself starting,
No.
looking here on Earth, from material that came essentially from, in quotes, outer space. Yeah.
Yeah, I think I'm with you there as well. My opinions changed over the years, but I
Mm,
firmly believe that life
ditto.
is out there, but I'm not necessarily, I
Yeah.
don't think the galaxy teems with bug-eyed monsters.
No.
Um,
Well, I mean, there's a fairly famous Fermi paradox, isn't there?
yeah,
Where the hell are they?
yeah, 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 absolutely. Wonderful. Thank you, Jim. Right, I'm going to hand over. Enough of my questions. I just hope somebody's got something they'd like to ask to Jim. Go ahead. It's yours to the floor.
Yeah, I've got one. Did I see an article or something about the changes or the amino acid chirality being linked to magnetism?
Oh, yeah, that's another argument. But again, all the effects are so weak, whereas the circular polarization one, it's incredibly effective. And to say you can do it in the lab very easily. It's not at the kind of 1 in 10 to the 17 effect. It's kind of just very easy. We know, and it's not just in the Orion Nebula. All the nebulae that we've looked at, which would be similar to Orion, similar to where it's thought the solar system evolved, all of them have high degrees of circular polarization. So, it's, and we know these nebulae have an abundance of organic molecules. That circular polarization has got to be doing something. Um, so, yeah, magnetism, like the beta decay, is seen as an alternative, but it's weakish. Um, and I mean, there was another idea going back a few decades, I guess, where people are saying, well, yeah, okay, we like the idea of circular polarization, but let's have it here on Earth. And it's true that as the sunlight comes through the atmosphere, it does produce some circular polarization. But as the sun traverses across the sky, the sign of circular polarization changes, say, from left-handed to right-handed. Okay, so you've got a problem. So some wise guy or girl said, ah, yes, we know how it is. There's mountains like this, you see me, and there's pools of, gunge from which life evolved on one side of the mountain, which only sees the sun in the morning. So only sees, say, left-handed or right-handed, and the other side, there's nothing. But I mean, that's far-fetched. I mean, why they don't just accept what we said and forget it? But obviously not. Yeah. Mm.
If we've seen evidence in other nebula of circular polarization, is there any evidence in our region, or is it not possible from within the region to determine if there is any?
No, because of course the solar system is so different to where it formed from the nebula from which the solar system eventually evolved. So no, there is no linkage, as it were, between what we now see and from the nebula from which it formed. Apart from people believe that the nebula from which the solar system formed was one with a lot of high mass stars. And the argument is that it's high mass stars which go supernova. So, and supernovae produce particular elements. And people believe that the elements we see here on Earth are indicative that the solar system formed in a nebula in which high mass stars formed. Okay. Now, the linkage there is that when I said that nebulae in which we discovered high degrees of circular polarization, it is only in the nebulae which form high mass stars. Okay. So again, that seems to me kind of further argument to support, what we've suggested. Yeah.
And you said we don't know why it would be left or right circular polarization.
No, it would be, that is chance itself.
Mm-hmm.
So there could have been solar systems formed in, right-handed circularly polarized light or left-handed circularly polarized, and life forms would be equally, likely left or right. You wouldn't be able to differentiate. If you looked at a civilization which had evolved in a right-handed amino acid world, as it were, there'd be no way. Well, scientists could tell, but I mean, just by looking at people, you wouldn't be able to tell that it was right-handed amino acids. But it would be the ultimate contraceptive in the sense that a left-handed amino acid person meeting a right-handed amino acid wouldn't be able to procreate.
Incompatible.
That's one way of putting it. Yeah.
You read my mind.
So presumably the effect of the polarization is just on the surface of anywhere that may have amino acids. It doesn't go deep within the soil or structure.
No. It would be a kind of a surface.
Yeah.
This type effect. Yeah. So it would be. I mean, that will be affected by it. Yeah. Yeah.
And you said it's pretty effective. Is that meaning that if you've got a equal amount of left and right enantiomers, that it's, are we talking days, years, weeks for destroying one of them?
Well, it depends on how much circular polarization there is.
Right.
Not in the degree of it necessarily, but in the number of photons, as it were. So it's a pretty efficient process.
Mm-hmm.
It does need to be, or preferentially, it's ultraviolet circularly polarized light. Just as if you're out in the sun, it's the UV light which affects your skin cells. So UV is much more effective, but that doesn't mean that other radiation is totally ineffective. But UV is by far the most effective, as it is on our skins. Yeah.
Thank you.
Good stuff. Anybody else with a question for Jim? Yes, Pat, go ahead.
Yeah, if the handedness of the circular polarization is a matter of chance, should that mean that there would be roughly equal areas of space exhibiting left-hand and right-hand polarization?
Yes, yeah. In fact, what actually happens is that you get a kind of quadrupolar picture. So I probably should put it on that slide. I don't know, I haven't, because we have kind of left and right. If you remember the image of the Orion Nebula, in fact, you get left, right, left, right. So you get four, two lefts and two rights. Yeah, yeah. But again, they're very distant from each other, and they tend to, as I've said a few times, be very large relative to the size of a typical solar system. Yeah.
Thank you.
Okay, anybody else? Or are we done with Jim? Okay.
Oh, thank you.
Well, Jim, once again, everybody, can I ask you to do the usual? Let's please show your appreciation, virtual hand or a clap or both. Thank you, Jim. That was wonderful.
Okay.
Really
Right, well,
appreciated.
yeah.
As you can see, we're a small society, but we're very keen and fascinating stuff. We really thank you for allowing us to record that as well.
No problem.
Okay, Jim, I'm hoping we can probably invite you back another time for something else. I don't know, but I'm sure you've got other subjects. I know I looked at your resume and you're on the Astro speakers list, so perhaps we could do something else again another season.
Okay. Yeah.
But in the meantime, thank you ever so much. That was really wonderful. Really appreciate it.
Thank you.
No, thank you very much, and bye-bye to everybody. Bye-bye.
We'll see you. Bye-bye, Jim.
Bye-bye.
For those that remain, just briefly, Sue, is Sue still there? Yeah, Sue's still.
Yes, yes,
She was
I'm still
asking
here.
about May. As you know, we have our next meeting is the 4th, is it? Anyway, it's the first Thursday in April. I think it's the 4th.
Yeah.
And we've got Mike Leggett talking about the solar system. Some of you joined after I'd stopped the screen showing our upcoming meetings, but they're all on Martin's wonderful website that he's done for us, so you can see what's coming up. On the subject of May, by May I mean the Kindle Centres. Most of you know we have our Zoom meetings, 9 I think a year. The 10th one is we have an AGM, or there isn't one in August, so there's 9, and the other 2. Yeah, sorry, the AGM is at the Kindle as well. But we have 2 or 3 meetings at the Kindle, and May is a kind of should we, shouldn't we? If Chris, oh, he's gone. Chris Badley's just gone, unfortunately. I was going to ask him something, but he's gone. Okay, he said he was going to be in Mexico for the eclipse. So I was going to ask him if he might want to help me out, and I'll bring some photographs back from Texas, and maybe we could do that, something, I don't know. I don't want to bore you all just with Chris's eclipse tour. I did that once before. Last time, quite a few people went to the eclipse, but it looks like I'm one of the few this time. But I'll separately contact Chris Badley and see if he wants to join with me and do a few photos from his experience. So there we are. So sorry I didn't get to say hello to everybody. Rob, wonderful head growing out, horse's head growing out the back of your head there. Fantastic. So there we are. Has anybody else got anything to add before we close? Questions or?
It's just a question of sorting out. I'm away in April, and, and I've got to give them some information at the Kindle.
Okay, well,
shall I leave it with you, Chris?
Well, you and I will chat between. I've got another 3 weeks before I bugger off to the States, but I will get in touch with you, and I'll speak to Chris and see if he can do something, and we'll see if anyone else is doing anything about the eclipse. But I'm hoping I come back in one piece. I've been told, I'm under strict instructions from my wife not to talk politics, and especially,
No
especially,
Trump. No
especially
Trumps.
in Texas and Arkansas, do not mention Trump, because I think I'm on dodgy ground.
Unless you're playing cards, of
Yeah,
course.
we're hoping to meet up with a couple that we only met for a couple of days in Wyoming in 2017 for the eclipse previously, and they're from Colorado. And as those of you who've been watching the news, you remember Colorado was one of the states that said that they would ban, on the state legislature said that they would not allow Trump to submit his candidature for the Republican Party, and that's now been overruled because they've said it's a federal issue, not a state issue. So sadly, Colorado's got to allow Trump onto the the voting register. But I'm praying that our friends from Colorado, from Denver, we never discuss politics with them. I have to subtly kind of pussyfoot my way around, and because we're going to have dinner with them and we're going to look at the eclipse together. I just hope they don't turn out to be raving Trump supporters, because it would be so embarrassing. So we'll try and find out some way, but I'm going to keep stum. I'm mainly in the southeast United States, the Carolinas, Virginia, Georgia, Arkansas, Tennessee, Texas. So I really need to keep stum.
Yeah.
But hey, you all know me. I'm a very quiet, shrinking violet. I don't talk very much anyway, so I shouldn't be in any problem, should I?
If we hear a news story about somebody
Yes.
being ejected from the States, then we know.
Oh, Christ. Yes. Anyway, there we are. Okay, so 4th of April, I'm not around. Keith, would you kindly host?
Yeah, no problem.
Okay, or anybody else, Keith, with Mark, with Martin, whatever. But I'll leave it to you mainly, okay? And if you need any help from me with the Zoom, but I think you've done it before, you can access the Zoom and
yeah.
But I will put out the
Right, finished.
I'll put out the link for you in advance so that you know, so that you've got it. Okay.
Yeah. Good.
You don't have to activate it, obviously. All right. Thank you, everybody, for attending. Hope you enjoyed it.
Yeah, it was good.
And
Thank you.
I'll see you.
Thank you.
I'll see you on the other side of the eclipse.
Yeah, well, hope you enjoy the eclipse, Chris.
I will. I'll try to.
Yeah.
If I,
Yeah.
I'll try. Okay.
Cheers.
I'll
Bye-bye.
see you in May. Bye-bye. Bye.